Okay, future engineers, we have another problem here. No, this is also involving a single degree of freedom structure for our free vibration response. No, we have here in a problem. In a figure, it is observed through the experiment that the amplitude of free vibration of a certain single degree of freedom structural system decreases in 5 cycles from 55 millimeters to 17 millimeters. And then afterwards, we are asked to find the logarithmic decrement delta, damping ratio psi, columns collective stiffness k, and damp angular frequency omega, damping coefficient c, and the damp angular frequency omega d. Okay, so here no, actually we have a figure, but let me draw the figure of a single degree of freedom system. So here no, it is assumed that the columns are having a fixed base support. And then the roof here for our SDOF is that this is infinitely, or this is a rigid roof. Next, what else? What do we have here? We're actually given also, no, there is another additional given. We have a mass equal to 1,223.242 kilograms. This one in the figure, the length of this one is equal to 3.5 meters. The elasticity of the column is 200 gigapascal. What else do we have? And then we have we're also given the dimension of the column. So the column is a rectangular tubing. So it's a base, height, and thickness. This is the base, this is the height, and then we have the thickness here. So that is equal to uh, 75 millimeters by 150 millimeters by 10 millimeters. And then natay given no natay in 5 cycles daw kuno initial displacement niya is 55 millimeters, and then after 5 cycles the amplitude of the displacement became 17 millimeters. Now we're asked to find the logarithmic decrement. So dali na siya. If you remember, the delta logarithmic decrement is equal to the natural logarithm of ui over u plus 1, or equal to 2 pi psi omega over omega d. So take note that this is the amplitude of two successive peaks. No, binsaon man ni nato nga ang given is not two successive peaks. So dapat if we have u naught, dapat next na itong gagamiton is the u1. Or if we have u1, next gamiton is u2 because it is required that we use the two successive peaks for our logarithmic decrement. So, ito may bato na ito na. So, actually, dali na, no? We're given with 5 cycles. Not na lang ang pamagi, we can use exponential or raise the power, square, take the root, etc. So, dali na ni siya. For this one, the logarithmic decrement is just equal to the natural logarithm of the initial displacement or the amplitude over the final, katong u5, over divided by the number of cycles. So for this one, you have the natural logarithm of 55 over 17 over 5, since 5 cycles man. And then delta will just be equal to 0.2348. Oh, we already have our logarithmic decrement. So, dali na kayo. Next is we were asked to find the damping ratio. So, if you remember no, natin dua ka formula ni logarithmic decrement. We have this one and also this one. So, the logarithmic decrement is equal to 2 pi psi omega over omega d. Now, we have here 2 pi psi omega over omega d. Let's proceed to the next page. Okay, I will just take note it here, no, that our logarithmic decrement is equal to 0.2348. And we know that the logarithmic decrement is equal to 2 pi psi omega over omega d. Now, saan mo na nato? If you remember, the damping coefficient is equal to the damping natural angular frequency is equal to the undamped natural frequency times 1 minus psi squared. And if we ratio the natural over the undamped natural angular frequency with the damped natural frequency, we will have 1 over 1 minus psi squared, square root of 1 minus psi squared. So this equation here, the delta becomes 2 pi psi times 1 over square root of 1 minus psi squared. Now, what do we do next? We will have, if we cross this on this side, we will have that the delta over 2 pi times 1 minus psi squared is equal to psi. My mistake. Rather, we just equate that, we just cross that here, and then the delta on the other side. So we will have square root of 1 minus psi squared is equal to 2 pi psi over delta. So let me rewrite the equation. We have the square root of 1 minus psi squared is equal to 2 pi over delta psi. Now, if we square the whole equation, we will arrive at 1 minus psi squared is equal to 2 squared pi squared over delta squared psi squared. Or simply, we will have 1 minus psi squared is equal to 4 pi squared over delta squared psi squared. If we transpose psi on the right hand side, we will have 1 is equal to 4 pi squared over psi squared, delta squared psi squared plus psi squared. And we can factor out the psi. We will have 1 is equal to psi squared times 4 pi squared over delta squared plus 1. We have 1 is equal to psi squared times delta squared over 4 pi squared plus 1. Sorry. This is 4 pi squared over delta squared plus 1, or psi squared times 4 pi squared plus delta squared over delta squared. Then eventually we will have psi squared is equal to delta squared over 4 pi squared plus delta squared. So one should be crossed on the other side. And then you subtract the square root both the left and the right hand side. We'll arrive that our psi, or the damping ratio, is just equal to the square root of delta squared over 4 pi squared plus omega squared. Since we have the logarithmic decrement delta, masolve na nato si damping ratio. Our damping ratio psi is just equal to 0.2348 squared over 4 pi squared plus 0.2348 squared. Our psi will be equal to 0.0373. So it means that our damping coefficient is 3.73% of the critical damping. Next, we are asked to find the collective stiffness K. So K is equal to 12 EI over L cube. So take note no nga dili na siya always na 12 EI over L cube. Now, if our SDOF is fixed, and then this is our L, so our stiffness there is 12 EI over L cube for each column. But, let's say the other one is fixed and the other one is pin. The pin part, yung stiffness is equal to 3 EI over L cube, while the other one has this is stiffness 12 EI over L cube. So in order to solve the K, we have the elasticity, which is equal to 200 gigapascal as given. Our length is also at 3.5 meters, but the I is not given. So we solve for I. Our I is equal to, if you remember, you have a rectangular tube with B, H, and it has also a thickness T. So that is equal to 75 millimeters by 150 millimeters by 10 millimeters thick. So our inertia, since we don't know the configuration sa atoang structural system, no, we know that this SDOF actually is three-dimensional. And then, di ta sure if ani ba ang itsura niya or this one. So whatever be the case, aron mas safe ta, i-assume na to ang weakest nga inertia or yung weak nga side. So if you tanawon, no, for this example, the inertia will be BH cube over 12. If the movement or oscillation is on that direction. But if the oscillation is on that direction, then it is safe to assume that our inertia should be the lowest or katong pinakagamay, that is equal to B cube H or HB cube. So we will have a 75 millimeters cube times 150 millimeters over 12. But take note that this is a hollow tube. Therefore, we need to subtract the hollow part because only the solid part resists the movement, no? So we have a 75 minus 20 times 150 minus 20. Sir, ani gikan ang 20? So we have a thickness here at 10 mm and thickness here at 10 mm on this side. So 10 mm plus 10 millimeters na thickness, that is a total of 20 millimeters nga deduction sa iyang width and sa iyang height. So we'll arrive at the I is equal to, so don't forget no nga naka-cube ni siya on this side. So we'll have 3,471,041.667. The unit is in millimeters to the fourth. Since itong ginagamit is in meters man, and since may naka-indicate diya, highly safe to convert the moment of inertia from millimeters to the fourth into square meters to the fourth. So you just divide that by 1000 to the fourth, and we will arrive that our I is equal to 0.000000347 meters to the fourth. So we have already our K, which is equal to 12, times our E, that is 200 times 10 to the 9 Newton per square meters. So we convert that into meter, ang I or ang inertia, it is because not a unity of our units. 3.471, nadiniwan diri 71042 times 10 to the negative 6 meters to the fourth power over the 12. So natay stiffness nga that is not 12, but rather L cube over L cube over 3.5 meters cube. So you have a stiffness equal to 194,297.376 Newton per meter. But collective stiffness daw. So nakalimot ko indicate no that there's a naging diri nga this is for one column, and since there is 4 column, the collective stiffness is equal to 4K or our K equivalent. So that becomes, just multiply that by 4, then we'll have a collective stiffness equal to 777,189.504 Newton per meter. So this is the collective stiffness of the system. So we have already our logarithmic decrement, the damping ratio, collective stiffness. Now we can solve our omega undamped angular frequency. So our undamped angular frequency omega is just equal to the equivalent stiffness over the mass. Our equivalent stiffness is equal to 777,189.504 Newton per meter over the mass, that is equal to 1,223.242 kilograms. And we'll have an undamped angular frequency equal to 25.2062 radians per seconds. Next is we're asked to find the damping coefficient, C. So saan mo na nato pag-find ko ang damping coefficient? By using psi, which is equal to C over 2 omega. So our damping coefficient C is equal to psi times 2 times the mass times the undamped angular frequency. So we have our damping ratio 0.0373 times 2 times the mass 1223.242 kilograms times omega 25 point, this is point, this is not 1,000, that is a point, 25.2062 radians per seconds. So may tabo na lang tayo coefficient nga of damping equal to 1629 Newton seconds per meter, or 2,300.1629 kilograms per seconds. So whatever your answer is, if it is in Newton seconds per meter or kilograms per seconds, both were right. And RF, the damped angular frequency, that is equal to omega d is equal to omega and square root of 1 minus psi squared. We have 25.2062 square root of 1 minus 0.0373 squared. Our damping or damped angular frequency just equal to 25.1887 radians per seconds. So if you notice, no, doon kayo si damped angular frequency with the natural angular frequency. So nalailiga sila no nga kuan. Wala na gid. Same din sila nga 25 radians per seconds. Lalo din sa decimal places ang ilaang difference. Okay, so this is an example of again no SDOF and then underdamped system. But lahi yung pamagi pag-solve instead of the equation of motions, we use the logarithmic decrement in determining the damping ratio and then the damping coefficient of our structure.